So in this presentation, we are going to look at Burke's theorem, and this is an important result in queuing theory, okay? Particularly in the context of MM1 queues, okay? So Burke's theorem is an important result in queuing theory, particularly in relation to MM1 queues, which you just said. And those are single server queues with an exponential inter-arrival times and service times. Great. Okay, so those are the key things this is sort of key sort of setup that we would use when we're sort of working with queuing theory, getting the hang of it for the first time. Probably the first section of queuing theory course is an MM1 course. And really, it's worth introducing Burke's theorem in its own right, rather than just giving it a sideways mention in a worked example, because it is something you probably will find very useful and will rely on it in an exam question where you won't be explicitly told it, but you will sort of be expected to know it and get to reference it. Little's law is another example of this. So Burke's theorem and Little's law are two sort of really key results that you should know about when you're tackling queuing theory for the first time. Anyway, I'll do something separately in Little's law. But anyway, just keep going with Burke's theorem here. Okay, so I'm just going to read these out. So Burke's theorem states that for an MM1 queue in steady state, the departure process, this is number one, departure process. The process of jobs leaving the system, this is a Poisson process with the same rate as the arrival process. Okay, so if jobs arrive at the rate lambda, they will also depart at the rate lambda. Okay, so particularly this is where it comes up quite often for me, or where I notice it the most, that this is how you relate something. Let's say you're asked in a worked example about something to do with departures. This is how you will probably relate it to information that you're given in the exam question or the tutorial question, because you probably will be given an arrival rate or something that allows you to figure out the arrival rate. Okay, so Burke's theorem allows you to sort of use that information further. Okay. Queue length distribution, the number of jobs in the system, i.e. the queue length in an MM1 queue in steady state follows the geometric distribution. This means the probability of having n jobs in the system is given by this the following value here, where capital N is a geometric random variable and n is an integer value with all the possible values of n. P of n equals 1 minus rho times rho to the power of n. And rho equals lambda divided by mu, which is service rate divided by arrival rate, or vice versa. Arrival rate divided by service rate. And this is the traffic intensity ratio. There we go. Ratio of arrival rate to service rate. Okay. And finally, residual service time. The residual service time remaining for a job currently being serviced in an MM1 queue is also exponentially distributed with the same rate parameter as the service time. Okay, that's fine. Okay, so just where we might pop up, where Burke's theorem might pop up. So just a couple of applications here. Okay, so systems analysis. Burke's theorem allows for a simpler analysis of queuing systems, providing the properties of the departure process and the queue length distribution. That's usually what I was getting at there earlier on. Usually what you're given is in an exam question, let's say arrival rate and service rate. This allows you to sort of answer questions further to it if it's an MM1 queue anyway. Network queues. In networks of queues, Burke's theorem helps in understanding the flow of jobs between different queues, as the departure process from one queue can be used as the arrival process to the next queue. Great. So, quick example and we'll wrap it up. Example, if jobs arrive at a rate of 10 per hour and the service rate is 15 per hour, then according to Burke's theorem, the departure rate process is also a Poisson process with a rate of 10 jobs per hour, and the number of jobs in the system follows a geometric distribution with parameter rho equals 10 divided by 15, which is 2/3. Okay, so that is arrival rate divided by service rate. Okay, that's it, I think. Yeah, we'll leave it there. No, I'll just check. Yeah, we're good. Okay.